Mathematical problems involving equations of the form ax equals b, where A is a matrix and x and b are both column vectors, are problems in linear algebra, sometimes called matrix algebra. Engineering and scientific disciplines are rife with such problems. Thus, an understanding of their setup and their solution is a crucial part of the education of many engineers and scientists. As we'll see in this brief introduction, MATLAB provides a powerful and convenient means for finding solutions to these problems. So in this lecture, we're going to be dealing with equations like this one. Well, if a, x, and b were all scalars, like 5 times 2 equals 10, this would be as easy as ABC. Well, as AXB. But we're going to be doing something more interesting than that. We're going to be focusing on cases in which A is a matrix and x and b are both vectors. In that case, there's a lot going on behind the simple facade of A times x equals b. First of all, as you know from the rules of matrix multiplication, if we show the elements of A and x and b, it's going to look something like this. If you recognize this particular layout, then you might have read our book, Computer Programming with MATLAB, because I copied it straight out of the Advanced Concepts chapter. Wait, you know what? Maybe I'm being a little lazy here. If you're going to do something, you do the very best you can, right? Shouldn't I show you something a little better than this tired, old, used rendition of a matrix multiplication? Maybe a new version with some color, maybe even some animation. Nah, too much trouble. Anyway, as you can see here, x is a column vector whose height n must equal the width, not the height, of A. B is a column vector too, but its height m does equal the height of A. So now, instead of 3 quantities, we see that there are actually m times n quantities in A, n quantities in x, and another m in B. And it's more complicated even than that, because if you write out all the operations, you get this. Now we have not one, but m equations. And each one of these equations involves n elements of A, n elements of x, and 1 element of b. And there's something special about these equations. Those n elements of x are the same in each of the m equations. In other words, those n elements have to satisfy all m equations simultaneously. The standard way to say that is that these are simultaneous equations. And there's something else special about them. They're linear. Linear means that there are no unknowns multiplied times each other or times themselves. So, for example, you won't find x1 multiplied times x2 or x1 multiplied times itself. When equations have both these special qualities, they're called simultaneous linear equations. And since we're using algebraic expressions, you can also call them simultaneous linear algebraic equations. You could just as well say that they are linear algebraic simultaneous equations or some other permutation of these 3 adjectives, but don't do that. People will laugh at you. So the subject of this lecture involves simultaneous linear equations, and we will confront the typical problem that arises with them. That problem is to find the elements of x that will solve all n equations simultaneously when you're given the elements of A and the elements of B. When there are only 2 or 3 equations, you can do it with a simple hand calculator. But if we have, say, 5 equations, solving by hand is out of the question. We need power tools for the big jobs. And MATLAB is perfect for this job. But let's look at a simple example with just 2 equations. Here we have 2 simultaneous linear equations and 2 unknowns, x1 and x2. And as I said, we can solve these equations by hand. And here's the answer. x1 equals 3.5652 and x2 equals minus 1.6522. Now let's solve the same 2 equations with MATLAB. To solve them with MATLAB, we need to get them into the form of a matrix equation, like this. Here we've written the coefficients of the x's in matrix form, and the x's and the b's in column vector form. This single equation down here is equivalent to this set of two equations up here because of the rules of matrix multiplication. If you're not familiar with those rules, then you might want to watch the video named Arithmetic Part 1 in Lesson 2 of our introductory course. Okay, to work on this problem in MATLAB, we form a matrix A from the coefficients on the left sides of the equations, and we form a column vector B from the constants on the right sides of the equations. Now, because of how we've set up A and B, we can see that the two equations are equivalent to the single equation A times X equals B. But now what? If the variables in this equation were scalars instead of a matrix and two vectors, like, say, 5x equals 10, we could just divide B by A and get X. You know, like this. To put it more formally, we use the forward slash operator with the operands 10 and 5. For that matter, we could accomplish the same thing with the backslash operator by putting the operands in the other order, which I actually like better because the A and the B are in the same order as they are in the equations A times X equals B. In either case, A is in the denominator, which is suggested by the way A is tucked under the operator in each case. And each case works fine with scalars. We don't have scalars. We got a matrix and a vector. Let's see what sort of snarky red error message MATLAB gives us when we put a matrix in the denominator. No error. And these numbers look very familiar. Let's look at our hand solution again. Well, we just got the same answer with MATLAB that we got by hand. Could it be that simple? We should probably check to see whether it's the correct answer. If these numbers are correct, then A times X has to equal B. Oh yeah, it's correct all right. And that, friends, is all there is to solving simultaneous linear algebraic equations with MATLAB. You put the coefficients from the left side of the equations into a matrix. You put the constants from the right sides of the equations into a column vector. And you divide the matrix into the vector with the backslash operator. Well, that's all there is to it for you, but that's not all there is to it for MATLAB. It has to do a whole lot of stuff in the background to get the answer. But you have to do nothing but divide a matrix into a vector by putting the matrix first, then the backslash operator next, and then the vector. By the way, the forward slash doesn't work with A and B, no matter which one comes first. And you could have figured that out from the compatibility rules that we gave you for the forward and backslash operators in our lecture on mixed mode arithmetic. But if you've forgotten them, please don't go back and run me again on them right now. I'm just not in the mood to go over all that again. The appropriate rules are that the operands must have the same number of columns for the forward slash and the same number of rows for the backward slash. In our case, A has multiple columns and B has only one, so the forward slash just won't work. But because there's one row of A and one row of B for each equation, A and B have the same number of rows, so the backslash does work. And if you correctly choose the backslash operator but put the B before the A, you get a row vector as an answer with the wrong elements. So use the backslash operator and put the A before the B, and you are guaranteed to get the right answer. Oh, and in case you'd like to see a larger problem, let's solve one with 20 equations and 20 unknowns. I'll use the function rand to help me gin up a matrix of coefficients and a vector b of constants, and I'll initialize it with rng so you can try the same thing with the same numbers. Here we set up a 400-element array A and a 20-element column vector B and solve for x. Then, to see whether x is a good solution, we calculated the difference between A times x and B, which is a 20-element error vector, and we assigned it to the variable e. Finally, we looked at the maximum absolute value in e, and I think you'll agree that 8.8818 times 10 to the minus 16 power is a very small error, so x is a very good solution. The backslash operation is a point of pride with MATLAB. It gives a first-class, world-class solution to any set of simultaneous linear algebraic equations. As we said in our introduction to this lecture, the solution of such equations is part of a branch of mathematics called linear algebra. And since its invention in the 1970s by Cleve Moeller, MATLAB has maintained a strong library of solutions to linear algebra problems. Indeed, Dr. Moeller himself was one of the developers of algorithms to solve problems in linear algebra when he invented MATLAB, and he incorporated those algorithms into it from its very inception. Most other programming languages, for example C, C++, Fortran, Java, provide no commands for solving this problem. Instead, the user of these languages must find a function written by other programmers or write their own functions to solve it. And writing a function to do this is no simple matter. By contrast, MATLAB provides an operator that solves the problem. You don't have to call a function at all. But if you really want to call a function, you can call mldivide, which stands for matrix left divide, and it gives exactly the same result as the backslash operator. So by now we've probably convinced you that it's easy to get a good solution to a set of simultaneous equations of the form A times x equals b. In fact, it's extremely easy. You might even say suspiciously easy. And in some cases you would be right. You might wonder why I'm saying good solution instead of just solution. I'm saying that because in some cases the solution that you get from MATLAB is not so good. It's not because MATLAB has made a mistake or has a bad algorithm. Not a bit of it. MATLAB's algorithm is extremely good. When the solution is not good, it's because it's not possible to get a good solution. This situation surfaces when there is inconsistent information in the inputs, that is, in the matrix A and the vector B. Let's start by looking at a simple example of inconsistent information. For example, these two equations, 4x1 plus 5x2 equals 6, and 4x1 plus 5x2 equals 12. Both equations have the same left sides, but different right sides, so they are clearly inconsistent, and no solution exists. So what does MATLAB do when we try its all-powerful backslash operator on these equations? Does it choke? Give an error? Catch our computer on fire? I always keep a fire extinguisher handy, so let's try it. Well, I don't smell any smoke, and we got only a warning instead of an error. Warnings are less serious than errors because they don't stop a function from executing. A message shows up, but the rest of the calculation keeps going. This warning says that the matrix is singular to working precision. When the matrix is singular, it means that the set of equations that it represents cannot be solved, no matter what's on the right sides of the equations. It warned us about the problem with A, but the calculation continued, and the answer it gives for the B vector that we gave it is minus infinity and infinity. So what the heck does that mean? Well, to understand it, it helps to visualize the equations on a two-dimensional plot. We can visualize any equation that has only two unknowns. We just plot pairs of values for x1 and x2 that satisfy the equation, with x1 on the horizontal axis and x2 on the vertical axis. To do that, we solve the equation for x2 in terms of x1. We give x1 a range of values, calculate x2 for each of those values, and then plot the results, like this. So here on the first line, we assigned x1 a vector of values from 0 to 10, spaced out in steps of 0.01. And then on the right side of the second line, we've solved the first equation for x2 in terms of x1 and set x2 equal to a vector of points that correspond to the x1 points, such that each pair of points satisfies the equation. Finally, we've plotted all these points using the plot function. As you can see, the points form a straight line, which is a consequence of the fact that we're plotting a linear equation. And for this plot, as x1 goes toward plus infinity, x2 goes toward minus infinity. And as x1 goes toward minus infinity, x2 goes toward plus infinity. Now let's look at the other equation. We'll use the same x1 values, but solve the second equation for x2 instead of the first one. And now let's plot x1 versus the new x2. The new line is the orange one, which is parallel to the blue one, but displaced upward by 6/5. So, okay, we visualized two simultaneous equations. But how does seeing them plotted help us understand the solution that MATLAB gave us of minus infinity for x1 and plus infinity for x2? Well, ordinarily when we look for a solution to simultaneous equations by plotting them, we're looking for the point at which their lines intersect. When we find that point, its x1 and x2 values are the solution we're looking for. But here's the thing. These are parallel lines, and the point at which the parallel lines intersect is, well, nowhere. They don't intersect. But if they were just the tiniest bit slanted relative to each other, we would know that they would intersect somewhere, either way off to the right or way off to the left, and the less slanted they were, the farther the intersection point would be from the origin. Well, now let's remember exactly what the hole warning said. Matrix is singular to working precision. The working precision it's talking about is double precision because that's the type of our matrix. And MATLAB is telling you that there may be some round-off error causing the matrix to appear to be singular. But if it's not singular, then it means that instead of being parallel, these lines are tilted just the tiniest bit. And it's such a tiny bit that the solution is so far away from the origin that the magnitudes of x1 and x2 are greater than the largest number a double precision variable can hold. And in MATLAB, any number greater than the largest number a double precision variable can hold is INF, which, as you know, is its representation for infinity. The same holds for single precision, too. And what does singular mean? Well, in general, it means special, and that's true here too. But for a matrix, the special thing is that its determinant is equal to 0. The determinant of a matrix is a single number calculated from all the elements of the matrix. And some algorithms for solving simultaneous equations involve dividing things by the determinant. When you divide a non-zero number by 0, the result is infinity with the sign of the non-zero number. And that, or the equivalent, is what happened here. We can get some meaning from the signs of these infinities too. Remember what we said about the blue line? That is, as x1 goes toward plus infinity, x2 goes toward minus infinity, And as x1 goes toward minus infinity, x2 goes toward plus infinity. Well, the same thing holds for the orange line too. So as these lines get closer and closer to being perfectly parallel, their intersection point x1, x2 approaches either plus infinity and minus infinity, or minus infinity and plus infinity. When MATLAB calculated the solution, it happened to get the second case, but either one tells the same story. Since the signs are opposite, the lines are parallel and sloping downward to the right. So the lines for our second set of equations never intersect. In other words, they intersect at infinity. In other words, they have no solution. Yes, MATLAB gave a solution when there was no solution, but it's not incorrect information, it's additional information. Now let's do the same thing with equations that do have a solution, like our first set. And now you know the drill. We get an expression for x2 in terms of x1 for each equation, which defines a line for each equation, and then plot both lines on the same graph. It's easy to see that these two lines do intersect. And to see that the intersection point is the solution to the equations, let's solve them with the backslash operator just as we did before, but this time plot the solution on the same graph with these lines that represent the equations. The solution to the consistent set is a normal pair of numbers, and the solution to the inconsistent set is a pair of infinities. That star is the solution, and it's right there at the intersection. So we've studied two examples of simultaneous linear algebraic equations, a consistent set of equations and an inconsistent set. We plotted the lines for the equations and saw that for the consistent set they intersect, while for the inconsistent set they do not. So is that always true? Do the lines cross if and only if the equations are consistent? Well, no. We're now going to look at a set of inconsistent equations whose lines do intersect. And here they are. You might notice a couple things right off. First, although, as I just said, these are inconsistent equations, the title that we've chosen for them is Overdetermined Equations. And second, there are 3 equations here instead of 2. We still have just 2 unknowns, x1 and x2, but we've used them in 3 equations. This is our first example of simultaneous linear equations in which we have more equations than unknowns. In this case, and in almost every case in which there are more equations than unknowns, there is no set of values that will solve them. You might recognize the first 2 equations. They're the consistent pair that we've just plotted. We've simply added a third equation that's inconsistent with the other 2. Since we've already plotted the lines for the first 2, we can just add the line for the third one. To see the reason for calling them overdetermined, note that each pair of lines intersects, the intersection points are all different, and each intersection determines a solution to one pair of equations. In fact, one of those 3 intersections is still marked by the asterisk that we plotted at the intersection of the first pair of lines. We don't need that now, so let's get rid of it. Alakazam, alakazam, useless asterisk, be gone. There. I've noticed that for some reason incantations don't seem to work unless they rhyme. And they can have side effects, like that purple line just changed to yellow for some reason. But the fact remains that instead of having just one intersection, we have 3 different intersections, each of which determines a different solution to a different pair of equations. So, these 3 equations determine 3 different solutions when we're looking for just one, and that's why we say the equations are overdetermined. If all 3 lines intersected at the same point, the equations would not be overdetermined, and that intersection would be the solution. But they don't, so no solution to these 3 equations exists. and that is almost always the case when you have more equations than unknowns. So what would happen if we were to ask the backslash operator to find that non-existent solution? Well, I've still got my fire extinguisher right here, so let's find out. Well, what do you know? Once again, MATLAB gives a solution when there is no solution. But this time it doesn't give us infinities. This time the solution looks perfectly normal. So what is this so-called solution? Well, to answer that, let's start by plotting it. As you can see, the solution that Mr. Backslash found is not at any of the intersections. It's not even on any of the lines, so it doesn't solve even one of the equations. But you have to admit it's pretty close to all of them. And that closeness is no accident. MATLAB's solution to a set of overdetermined equations is the one that comes the closest to solving all three equations simultaneously, where closest is defined in a special way. To see what that special way is, let's look at the error in its solution. You remember how we calculated the error for that set of 20 simultaneous equations and 20 unknowns? Well, let's do that same thing for this solution. As for the case of 20 equations, the elements of E are the errors for each equation. And for this case, there are 3 of them. But now, instead of looking at the error with the maximum absolute value, which in this case equals 0.9934 and pertains to just one equation, which happens to be the second one, we're going to look at a measure of error that includes all the equations. It's called the squared error, and it equals the sum of the squares of all the elements of E. So this tells us that the sum of squared errors in the solution that MATLAB gave us, SSE, is equal to 2.2443. And now we can tell you the special way in which the solution to a set of overdetermined equations is defined. It's the one solution that has the least sum of squared errors. This means that you could try any other solution X in the universe and calculate SSE in the same way, and you will never find one that gives a smaller sum of squared errors than the one that backslash operator gives you. This method of solving a set of overdetermined equations is called the least squares solution, and it's the one that is most likely to be the best solution for any given problem in engineering or science that involves linear simultaneous equations. To put it precisely, the solution that MATLAB gives to a set of overdetermined equations is the one that is closest in the least squares sense to solving all of them. Of course, when there's a true solution, as you would expect when there are the same number of unknowns as equations, the error will be very small. To find out what very small means to MATLAB, you can look at the value returned by the built-in function EPS, which is short for epsilon, the Greek letter that stands for an arbitrarily small number in mathematical proofs. In MATLAB, it also stands for a small number, but it's not so arbitrary. Eps is the difference between the number 1.0 and the next largest number that a double precision value can represent. If the value of the sum of squared errors for your solution is more than, say, 1,000 times eps, then you can be almost certain that you've either typed something wrong or you're solving a set of overdetermined equations. Okay, it's time to take a little break with a fun little brain teaser. If a system with more equations than unknowns is overdetermined, what do you call a system with fewer equations than unknowns? Okay, time's up. It's underdetermined. And we're going to see what the backslash operator does with underdetermined equations right now. We'll do a couple examples. Our first example has one equation and two unknowns, and our second one has two equations with four unknowns. Before we look at the backslash solution to each one of these, let's think a minute about what to expect. To solve the first equation, it'll need to find two numbers such that twice the first one plus 10 times the second one equals 4. Well, if you ask me to do that, I'd be lazy and pick 0 for one of them and set the other one to make the left side equal to 4. Like say x1 equals 2 and x2 equals 0. Because 2 times 2 is 4 and 10 times 0 is 0. So 4 plus 0 is 4. Or maybe let the first one be 0 and the second one would need to be, let's see, okay, it'd be 4/10. Of course, I could pick any number for x1 and find the perfect x2 to make the left side equal to 4. I mean, you can see that there are infinitely many solutions. And as a matter of fact, with underdetermined equations, if there's any solution at all, there will always be an infinite number of solutions. But like I said, I'm lazy, so I'd go with a 0 for one of the unknowns because it's just the easy way. But now let's see what that hard-working backslash comes up with. Oh, what do you know? The old backslasher stole my idea. Let's try the second example. Look at that. 2 zeros. This backslash is a real operator. It took the doubly easy way out and set two of the unknowns equal to 0. And that, dear friends, is what it always does with underdetermined equations. It'll give you as many zeros as it can get away with, which is at least 1 for every missing equation. Here there are 4 unknowns and only 2 equations, so we would need 2 more equations to avoid having an underdetermined solution. So we got 2 missing equations. So word to the wise. If you see even 1 0 in the solution to simultaneous equations, and I mean an exact 0, like one of these, not just a tiny number like 10 to the minus 16, but an honest-to-goodness, no decimal, no negative power of 10, goose eggs, zilch, nothing, nada, 0. Then you have probably got yourself fewer equations than unknowns. Or to put it another way, you probably got a matrix with fewer rows than columns. You know, a height less than its width, a short stack, landscape mode, a wide load. That may be exactly what you should have, but it usually isn't. It usually means something got left off somewhere. Well, we've got one more topic to cover in our introduction to solving linear equations with MATLAB, and it comes with a warning. It's not enough to blindly accept the solution that MATLAB provides, even if there aren't any zeros in it. We need also to consider the stability of the solution. What does that mean? Well, the most common measure of stability is the effect for a given set of equations ax equals b that changes in b have on x. This stability issue is confronted by engineers and scientists when a problem of the form that we've been looking at, in which ax equals b must be solved for x, and the elements in b are measured values. Any measurement is subject to error. And if small errors in those measurements cause the calculated values of x to change drastically, then we've got a problem. The problem is with the matrix A. And when it happens, the matrix A is said to be ill-conditioned. So what do you do about ill-conditioning? Well, first off, you need to know when you've got it. One way to do that would be to solve for x and then make some very small changes to the elements of B and solve again. If you change the elements by 1% and x changes by, say, 50%, then A is ill-conditioned. If x changes by only, say, 2%, then A is well-conditioned. Of course, you might be lucky and make changes that have only a small effect on x. To do a better job of testing, you might repeat this process hundreds or even thousands of times, making small, randomly selected changes, but you'd never be sure that you'd seen the worst possible case. But there's a better way, and it's a far easier way. MATLAB provides a function called cond, which is short for condition, that will look at your matrix and tell you how ill-conditioned it is. Let's try it on a couple different sets of equations. These equations look more like what you would expect in real-world problems, because the numbers aren't all integers like in our simplified examples. And we have two examples here, each one of which has two equations and two unknowns. We're going to find that one of these sets of equations is very ill-conditioned, while the other is perfectly well-conditioned. But you can't tell any of that by just looking at them. So let's ask MATLAB, which can see right through to the heart of the problem. Okay, so the condition number of the matrix for the first set of equations, which I've called A1, is 2.9640. Now let's do the second set. Okay, well, A2's condition number is 94,574, and that's a lot bigger than 2.964. So which one of these is ill-conditioned? Well, to answer that, you need to know whether a bigger condition number is better or worse. Which one do you think it is? Well, I won't keep you in suspense. Bigger is worse. The condition number for each set of equations is the maximum factor by which the percent error can increase from the inputs to the outputs. Since we don't want to increase the percent error from the inputs to the outputs, smaller is better. The outputs are the elements of x. And what are the inputs? Well, in the typical scenario, the coefficients on the left of the equations are calculated, whereas the values of the constants on the right are measured. Thus, the inputs are those constants on the right. So, for example, if the typical error that you would expect in measured values on the right of the equations is, say, 1% for each of these two examples, then the error in the output x for the first example will be no bigger than 2.964%. But for the second example, the error in x could be as large as 94,574%. The breakpoint from well-conditioned to ill-conditioned depends on the percent accuracy that you need for the outputs versus the percent accuracy that you can achieve for the inputs. More precisely, it's equal to the maximum percent error that you can tolerate in the outputs divided by the maximum percent error that you expect in the inputs. If you can tolerate an error of roughly 3% and you've got 1% accuracy in your inputs, then the first set of equations is well conditioned. But there is no conceivable scenario in which you could accept a 94,000-fold magnification of error, so the second set of equations is definitely ill-conditioned. Let's look at some example input errors for these equations and see what sort of output errors we get. Let's solve the first set of equations to start. Now let's add a small error to B1 and get a new input vector. Let's calculate the percent error in the input. The percent error is equal to 100 times the magnitude of the error vector divided by the magnitude of the original vector. So we have about 1% error in our input. We use the norm function here and here because we want to get a number for each of these vectors that represents its magnitude. The standard magnitude is the Euclidean length, which is the square root of the sum of the squares of the elements of the vector. And when we give norm a vector with no additional arguments, as we have here, it returns exactly that. So thanks, norm, and get ready because we're going to use you a lot. Now let's solve our equations with this new input vector. You can see that the output changed a little bit. Let's use norm again to calculate the percent change. Well, our output changed by just under 1.2%. According to our theory, this percent change in the output can't be bigger than the condition number for A1 multiplied times the percent change that we made to the input. Let's see that condition number again. And the percent change we made in the inputs was 1.0318. So let's check. Yep, 1.1930 is definitely smaller than 3.0583. So let's hear it from mathematics. And what about the second set of equations? The ones that are so badly ill-conditioned. Let's do the same thing for them. Start by solving the original equations. Once again, let's add that same small error vector to our input error vector B2. And calculate the percent input error. Again, we solve with the new input. And calculate the percent change in our output. Whoa, 2,389.1% error. Well, this is a disaster. It means that if the change we made in our input vector were the result of a 1% measurement error in the field, then the answer we would get as output would change by over 2,000%. To get an output error down to 1%, we can't tolerate more than 1/2000th% error in our measurements. I would not want to be the guy doing those measurements. Okay, let's check our theory again. What was the condition number for these equations? Oh yeah, over 94,000. Obviously, 2,389.1% output error is way below the limit, which is, let's see here, condition number times percent input error. Well, it's over 117,000%. Well, 3 cheers for mathematics. But boo to this second example of 2 equations and 2 unknowns. So now we understand how to check the condition of simultaneous equations and what the condition number means. So what do you do when the condition number is too large? Well, the answer is not to tell that person measuring the inputs to keep the error under 0.002%. The answer is to add 1 or more equations. The simultaneous equations that we get in science and engineering are determined from real-world problems. And typically, a real-world problem allows for the determination of additional equations. Suppose we had determined 1 additional equation for the second example, like, say, this one. Now we have an overdetermined system for our third example because we have 3 equations and just 2 unknowns. But we already know that our trusty backslash operator can handle that just fine. The question now is whether the matrix for this system, which looks like this, is well conditioned. And an equally important question is this one. Can the condition function handle a matrix with more rows than columns? Well, let's answer both questions at once. Well, it obviously can handle it, and this condition number is more like it. We can live with that. And if we can't live with an upper limit of 4.1781 as a magnification of percent error from input to output, we might be able to look at the problem again and figure out a 4th equation. I'm pretty sure that at this point you are exhausted and falling asleep. So I'm not going to do that same thing I did with adding input error and calculating the output error for the other 2 sets of equations for this set of equations. You can try that after you've had a nap. But I can tell you this. With this right side for these equations, the output error for a 1% input error will actually be less than 4%. So this brings to a close our introduction to solving linear equations in MATLAB. And in this introduction, we've seen how to solve a set of linear algebraic equations with the backslash operator, and we found that that clever operator works no matter whether the number of equations equals the number of unknowns, or is greater or less than the number of unknowns. And we learned the meaning of the condition of a set of equations and how to calculate the condition number. Gee, seems like I could have covered that in a lot less than, let's see here. Yes, 7 hours. No, wait, it just seemed like 7 hours. It was actually less than 50 minutes. Of course, you probably know that if you ask a professor anything, the answer is going to take about 50 minutes. Well, that is 50 minutes on Monday, Wednesday, or Friday. On Tuesday or Thursday, it'll take 75 minutes. Anyway, despite talking all this time, I've not even begun to scratch the surface of linear algebra. We didn't get to the inverse of a matrix, for example, or the pseudo-inverse, or singular value decomposition, or eigenvalues, or eigenvectors. All these topics and more are covered in a typical linear algebra course, and MATLAB has functions for all of them. It's worth spending a lot of time studying linear algebra because it's such an important topic. And why is it so important? Well, it's important because it just so happens that the vast majority of real-world mathematical problems in the universe that we live in are linear, or approximately linear, and many of those problems involve more than one unknown. If you haven't taken a course in linear algebra, then I encourage you to do so. And you can learn the basics in a few months, and then let MATLAB's functions do the heavy lifting for you. On the other hand, if you want to master the field so you can write your own functions, you're going to need to set aside a little bit more time, say approximately 1 lifetime. So if you're going to go that route, I recommend you get busy.